How many rogues are out there? To get real about risk, we have to count the dark. Not guesses, orders of magnitude with reasons behind them. Start with stellar evolution. For every massive star that ever lived in the Milky Way, there's a chance it ended as a black hole. Roll the galaxy star formation history forward, apply initial mass functions, and you land on a sobering range. Somewhere between 100 million and a billion stellar mass black holes drifting through the Milky Way. That's the background you never see, the fossil record of dead suns. But models only go so far, so we cross-check with a very different instrument, the universe itself ringing like a bell. LIGO and Virgo hear black holes collide. Those merge rates, when you fold in the volume of space they survey and how often they catch an event, imply a large hidden population. The mergers are the loud moments. Between them, most black holes are quiet. If coalescences happen this often, there have to be far more black holes not merging right now, living out long, dark lives. Now layer in dynamics. Black holes don't just sit where they're born. Some get natal kicks, momentum shoved into them by asymmetric supernova explosions. Others form by direct collapse with little kick but inherit the motion of their parent stars. Cluster dynamics can eject remnants, slinging them into the halo on plunging orbits. The result is a mixed population, some gliding with the disk, some cutting steep paths through it like hailstones through a roof. Speeds matter. In the disk, typical velocities are tens of kilometers per second. Halo crossers can run into the hundreds. That's the difference between a slow tide and a stone skipping across a pond. Faster lenses spend less time near any one place, give shorter windows for accretion and make alignments briefer. But they sweep more volume. Over millions of years, they pass through neighborhoods we care about. So what's the density near us? Here, S where uncertainty bites. Take the conservative end. Say 100 million black holes in a Milky Way with a stellar disk roughly 100,000 light-years across and a thickness of about 1,000 light-years. Smear that population realistically, more in the inner regions, fewer outside, and you still get a local number on the order of a few tens per million cubic parsecs. Push the upper population bound, shift some into the halo, and the local disk number changes, but not to zero. For back-of-the-envelope intuition, that can translate to roughly one stellar mass black hole within a few dozen parsecs at any time, with wide error bars. The bands matter. If the true count leans high, the encounter math shifts. If natal kicks are stronger than we think, more black holes spend their lives in halo orbits, making fewer slow passes but more high-speed grazes. If more form by direct collapse without kicks, they track the disk's kinematics and share the sun's general motion, raising the chance of longer, slower encounters that tug more gently but for longer. Meanwhile, another clue sits in how often we see microlensing events with unusually long timescales. Surveys like Ogle and MOA pick up thousands of lenses. Most are stars. A small tail stretches into longer events that could be heavier objects. When you fold in astrometric shifts from Hubble or Gaia for a subset, the mass distribution hints at a tail of dark lenses. It's not a clean census. Selection effects are everywhere, but the tail exists. What nobody knew when the first free-floating black hole was weighed was how these lines of evidence would start to converge. Gaia's extended mission pushes its astrometry into finer territory. Roman will stare at dense fields long enough to nail parallax on lensing events, separating stars from compact objects. Rubin's cadence will spray the sky with time-domain data, expanding the pool of strange light curves. Each new dataset will drag the error bars inward. There's another layer people don't like to talk about: survivorship bias in binaries. We find black holes easily when they feed from a companion. Those are the loud few. The quiet many never had a companion or lost it long ago. If you only count talkers, you miss the crowd. Population synthesis models try to correct for that, but they depend on assumptions about metallicity, star formation bursts, and kick distributions. Small tweaks swing totals by factors. So where does this leave the risk ledger? With humility. The Milky Way likely hosts hundreds of millions of stellar mass black holes. A fraction share the sun's general orbital radius. A smaller fraction pass within a few parsecs over million-year timescales. Shrink the distance to a light year, and the probability per million years drops sharply, but it doesn't vanish. The neighborhood isn't packed, but it's not empty. Here's the emotional core. The numbers aren't scary because they promise doom. They're scary because they erase false comfort. You don't need 1 in a million to be pointed at us. You just need 1 in hundreds of millions moving through the right patch of sky at the wrong time. And because most are dark, the only advance notice we get comes from gravity's fine print. If we miss that fine print, we trade certainty for luck, and luck is not a plan. Knowing the count is step 1. The fear, the hope, and the plan live in speed and trajectory. Where they go next writes our odds. The ways they hide, why we don't see them. Here's the part that messes with your gut. These things don't shine. A black hole gives you no photons, no surface, no silhouette unless it crosses something bright or eats something messy. Gravity is the only tell. That's why warning time collapses. You can stare straight at one and never know, unless a star behind it flinches. So we lean on the tricks gravity gives us. Microlensing is the loudest of the quiet methods. When a dark lens drifts in front of a distant star, the star brightens along a smooth curve and then fades. If the lens is heavy enough and the alignment is good, the event stretches over weeks to months. Pair that with astrometric lensing, the tiny sideways shift in the star's apparent position, and you can weigh the lens. But there's a catch. These alignments are rare. The lens, source, and Earth need just the right geometry. Miss the season, you miss the show. Accretion would make life easier. When a black hole runs into gas, it heats the infalling material and you get X-rays or radio. That's how we find black holes in binaries. Out in the field, though, fuel is thin. The local interstellar medium is hot and sparse, atoms per cubic centimeter. Bondi accretion from that soup is a trickle. You might get a faint radio whisper, maybe an X-ray transient if it cruises through a denser cloud. Most of the time, nothing. There's a more subtle signature, a dynamical wake. A massive object plowing through gas drags some of it along, leaving a denser trail. In principle, that wake emits. In practice, it's faint and smeared out, and the Milky Way is busy. You're trying to notice a ripple in a choppy sea. Even big radio arrays struggle to separate a black hole's wake from everything else glowing and hissing in the plane. Okay, what about the surveys? Gaia has phenomenal astrometric precision, but it's tuned for stars bright enough to measure cleanly, and it revisits on a schedule that wasn't built for microlensing alone. It still catches astrometric shifts, but only for certain magnitudes and timescales. Rubin will own the sky in cadence, nightly passes building light curves for billions of sources. That's perfect for flagging long, smooth lensing bumps. But Rubin's strength is also a blind spot. It needs a source to fluctuate. In the sparse star fields near the solar neighborhood, you just don't have the dense backdrops that bulge fields give you. Meanwhile, Roman will stare deep and long at crowded regions, measuring parallax across the telescope's own vantage in Earth's orbit. That separates compact dark lenses from stars more cleanly. But Roman's survey fields are chosen for microlensing yield, not for sweeping the whole sky for local drive-bys. If a rogue cuts across a quiet patch, Roman might never look. Even when you do catch a lensing event, the information is surgical. You get a mass estimate, a distance bracket, a proper motion on the sky. You don't get a beacon you can track forever. Once the alignment ends, the lens fades back into statistical darkness. Predicting its future path requires exquisite astrometry and luck with future background stars. For nearby rogues, backgrounds are sparse, so the next measurable alignment might be years, or never. Another reason they hide, confusion. Binary stars can fake lens-like light curves. Star spots can mimic slow drifts. Instrument systematics can push a centroid the wrong way. Teams spend months filtering false positives. A few % of ambiguous events can swing your inferred dark lens population from rare curiosity to common but quiet. That uncertainty isn't just academic. It sets how wide we cast our net. Add the cruel geometry of gravitational focusing. A fast lens bends trajectories more when it's close, but it also spends less time in the zone where we could see signatures. High-speed halo rogues blaze through with fewer opportunities to accrete or to line up behind multiple stars. They're the stealth jets of the population, loud in gravity, silent in light, gone before you look. So we're scanning a keyhole for a bullet. Gaia is our ruler for tiny sky wobbles. Rubin is our heartbeat monitor for light curves. Roman is our precision scale. Radio arrays and X-ray monitors are the motion sensors on the walls. Each has blind spots, cadence gaps, magnitude limits. Stitch them together and you still miss most of the galaxy, most of the time. That's the psychological trap. Great tools make us feel safe, until a quiet pass reminds us coverage isn't the same as control. That's the stakes in one sentence. If our sensors can't flag a rogue early, warning shrinks from years to months to nothing. Which leaves one practical question. If one actually swings by, what does the pass look like from out where our comets sleep? Anatomy of a drive-by, through the outer solar system. Start far out, so far that the sun is just another bright point. The Oort Cloud isn't a shell of packed ice balls. It's a vast, thin fog, trillions of comets on slow, cold orbits stretching tens of thousands of astronomical units. A rogue black hole doesn't need to come close to stir it. Tides get there first. Gravity doesn't pull equally. It pulls harder on the near side than the far side. That gradient is the quiet alarm. At around 10,000 AU, you don't get fireworks. You get statistics. The energy of those distant orbits is tiny. A small nudge changes everything. Pass a 7 solar mass lens through that regime and the cloud feels it as a long, low tide. Some comets are lifted, some lowered. A few get pushed onto trajectories where the sun's pull tightens its grip. They fall inward not all at once, but over decades and centuries, like a storm swell that keeps sending waves after the wind is gone. Closer, around 1,000 AU, the geometry shifts from gentle tide to discernible tug. Here, the rogue's passage is fast, tens to hundreds of kilometers per second. But the gradient across the Oort Cloud fragments it touches is stronger. Numbers turn into events. A fraction of bodies tip into long ellipses with perihelia diving toward the inner system. If the intruder's path crosses at the right angle, you get a spike in comet injection that begins years after the closest approach and echoes for centuries. At 100 AU and the scattered disk in the outer Kuiper Belt's fringe, the stakes feel personal. We have spacecraft out there. We also have large, slow-moving worlds with names and histories, Sedna-like objects detached and quiet. The rogue won't suck anything in. That's not how gravity works. It will pass, accelerate local bodies a bit, and leave. But a bit at those distances can mean ejections, captures, or gentle chaos. 1,000 tiny course changes that rewrite collision calendars long after the interloper is gone. Simulations tell the story better than metaphors. Set up a numerical experiment. Seed 10 million test comets in a realistic Oort Cloud distribution. Add planets. Then send a 7 solar mass object through on a hyperbolic path at 80 kilometers per second with a missed distance of 150 AU. Run it. What you see isn't an apocalypse. It's a redistribution. A small percentage is ejected entirely, trading the sun for the galaxy. A smaller percentage is dropped into long-period orbits with perihelia inside the planetary region. A vanishingly small subset gets captured into bound companions if the velocity and angle are just right, rare, but not impossible. Now add complications we didn't earn. What if the rogue is a binary, 2 compact objects gliding together? The tidal field gets lumpy, resonances creep in. A few test particles get unusually strong kicks when their orbital phases coincide with the binary's motion. Rare outcomes become slightly less rare. Still, the main story holds. Tides first, then scatterings, then a long tail of consequences. From a human vantage, the pass is anticlimax followed by patience. During the event, nobody on Earth feels a thing. No sky tear, no auroras, no global tremor. The accretion glow we'd crave likely doesn't appear. There's not much to eat that far out. The first hints arrive as numbers, a minor shift in the trajectories of known distant trans-Neptunian objects, a puzzling uptick in faint, long-period comets a decade later, timing residuals in outer planet ephemerides that refuse to average away. Here, S where the timeline stretches. A surge in long-period comets doesn't hit like a meteor shower. It rises as a background risk. Over 50 to 200 years, more comets with large perihelion distances get nudged into the inner system. Planetary defense pivots from near-Earth asteroids toward tracking cold visitors with long lead times and poor orbits. The night sky gets busier for survey telescopes. Civilizations don't get wiped. They get busier, then smarter, or unlucky if they ignore the statistics. The only real mistake is to treat a slow threat like it's far away. There's a quieter outcome hidden in the noise. Slight, cumulative orbit tweaks for outer planets are a constraint. High precision ranging to spacecraft at Saturn and beyond gives us daily truth serum on our gravitational model. A rogue that comes inside a few hundred AU leaves a tidal fingerprint in those residuals. If we don't see it, we can push the allowed mass distance box outward. That's how a drive-by becomes both a risk and a measurement. Meanwhile, local captures, if they happen, are stories for future astronomers. A tiny population of comets could end up loosely bound to the rogue for a while, then released with altered energies as it exits. That could seed asymmetric influxes decades later, adding structure to the comet shower that wouldn't be obvious without careful cataloging. It's tempting to ask about extremes. What if a pass hits at 100 AU dead-on? The solar system's architecture is resilient. Planets are deep in the sun's well. You'd see measurable perturbations in the Kuiper belt and scattered disk. You'd risk losing some minor bodies, and you'd boost long-period comet traffic for a significant chunk of time. But Earth doesn't get ripped from the sun. The atmosphere doesn't tear away. The danger is cumulative exposure to more impactors, not cinematic collapse. All of this loops back to warning. If a rogue crosses at 10,000 AU, the first signs are statistical and slow. At 1,000 AU, you might catch astrometric hints in outer planet data and plan for a century-scale comet uptick. At 100 AU, you DWANT probes retasked yesterday, outer sentinels measuring trajectories in real time, and a global plan to track new comets early. No suction, no roar, just gravity doing the quiet work that history remembers later. The odds, how likely is a close encounter? To weigh fear against facts, we need math that ties population to risk. The core idea is simple: how many rogues per volume, how fast they move, and how big a target you're drawing around the sun. Number density times velocity times cross-section. Then add gravitational focusing, because gravity fattens the target as objects speed by. Start with the geometry. Imagine a cylinder through space with the sun at its center. Any black hole passing through that cylinder with radius equal to our danger distance counts as a close encounter. If you set the danger radius at 1 parsec, about 206,000 AU, you're asking how often a rogue wanders within the broader outskirts of the Oort Cloud. Shrink it to 0.1 parsec, or even 1,000 AU, and you get stricter, scarier passes. The smaller the circle, the rarer the hit. Now plug in a plausible local density. Take a cautious estimate that gives you a handful of stellar mass black holes within a few dozen parsecs. Fold that into a characteristic speed, tens of kilometers per second for disk rogues, up to a few hundred for halo crossers. Multiply density by speed and by the area of your circle. Then correct for gravitational focusing, which effectively increases the radius because the sun's pull bends trajectories inward. Heavier, slower lenses are focused more. Faster halo objects shrug it off. So what drops out? For passes within 1 parsec, you get probabilities per million years that aren't zero. Over tens of millions of years, a brush at that distance becomes likely. Tighten to 0.1 parsec, roughly 20,000 AU, and the chance per million years shrinks, but across a billion-year horizon it still lands in the could-happen bin. Bring it down to 1,000 AU, and the math gets stingy. On human timescales, it's negligible. On geological timescales, it sits in the long tail, improbable in any given million years, not impossible across the deep past and future of the solar system. Here's a way to ground it. We already know stars pass close. Skal's star likely skimmed within about 0.25 parsecs some 70,000 years ago. Gliese 710 is projected to swing within roughly 0.62 parsec in 1.3 million years. Those are luminous catalogued objects. They announce themselves. Dark rogues, if present in similar or slightly lower densities, would add a silent layer of flybys we wouldn't have counted. Most would still miss by large margins. A few would graze the comet cloud. Vanishingly few would thread the inner outskirts. The key difference is detectability, not inevitability. A bright passerby can be modeled for centuries. A dark one needs a specific alignment with a background star or a tidal whisper in our ephemerides. That's why the risk is asymmetric. On paper, the odds for stars and rogues within a parsec can be comparable. In practice, one is watched, the other is. Gravitational focusing nudges the numbers but doesn't flip them. At high speeds, say 200 kilometers per second, the focusing term is small. At lower speeds, 20 to 40 kilometers per second, it grows, especially for heavier lenses. That makes slow, disk-bound black holes slightly more likely to wander deeper into our chosen circle than naive geometry suggests. But the biggest lever is still the radius you care about. 10,000 AU sees more traffic than 1,000 AU by a factor of 100 in area, before focusing. Uncertainty is the hidden protagonist. Change the local density by a factor of 3, and the encounter rate follows. Tilt the velocity distribution toward faster halo objects, and you get fewer long interactions but more quick grazes. Assume a clumpy distribution, more rogues near spiral arms or lingering around old clusters, and your local odds swing with the sun's position along its galactic orbit. The tails of these distributions do the damage. Rare combinations of slow speed, high mass, and the wrong trajectory dominate risk, even if they barely affect averages. So where does this leave us practically? On human horizons, centuries to a few millennia, the chance of a rogue diving inside 1,000 AU is so small you can live your life happily and be right. On civilization horizons, tens of thousands of years, the odds of a pass within 0.1 parsec are small but non-zero, with consequences that play out through increased long-period comets rather than instant catastrophe. On geological horizons, millions to hundreds of millions of years, encounters within a parsec are expected, and deeper passes move from rare to plausible given enough time. That's why the plan matters more than the panic. Unlikely isn't safe, it's a wager.